In this video, we're going to cover the tools and techniques that you can use for solving a specific kind of probability scenario called multi-stage experiments. For those who don't know me, my name is Chris Inozoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. Multi-stage experiments are a common type of probability question. These are the kinds of questions where there are multiple things that happen in sequence. The classic example is a sequence of coin tosses. Suppose I toss a coin 2 times in a row. What is the probability that I toss 2 heads in a row? This is the kind of question that's best solved using a tree diagram. Tree diagrams are a useful tool for dealing with all sorts of probability scenarios, but they are best used when dealing with a sequence of events. The standard tree diagram looks like this. For now, we're just going to ignore the specific notation that's used in that diagram and just focus on how it works by covering the earlier example. We always start our tree diagrams out by figuring out what are the possible outcomes in our scenario. In this case, it's quite simple. We have heads or we have tails. So what we do here is branch off from the outcomes of the previous coin toss and then add the possibilities of the next coin toss, which once again is just going to be heads or tails. Now that we have all the possibilities laid out in our tree diagram, we have to figure out the probability of each of those things occurring. In this case, it's quite simple. The probability of head or tails is always going to be 50-50. So when we look at that first set of branches, we have 50% for heads and 50% for tails. Now that we have the first set of probabilities written out, we now move on to the second toss. The good thing about coin tosses is that each toss in sequence is independent. It has nothing to do with what happened previously. So when it comes to labeling those probabilities, we're once again going to give 50% for heads and 50% for tails. And just like that, we've finished our tree diagram. Now let's look at how to use it. So, first question. What is the probability of tossing 2 heads in a row? Well, the only way that ever happens is if you toss a head on the first toss and then a head on the second toss. The way it works for tree diagrams is that you multiply along the branches that you want. In this case, we're going to multiply along the first head and the second head. So this will end up just being 0.5 times 0.5, giving you a final probability of 0.25. Okay, how about something just a little bit harder? What if I want to find the probability of tossing any head, whether it be 1 heads or 2 heads? Well, in this case, we have multiple possible outcomes. You could get 2 heads, like we calculated from before, or you could get 1 head on the first toss, or 1 head on the second toss. There's 3 possible outcomes here. The way we handle this is we're still going to multiply along each individual set of branches, but when you have multiple distinct paths to take through the tree diagram, you're just going to add the results at the end. So each given branch is still going to be 0.5 times 0.5, or just 0.25, but when you get to the end, you're just going to add those 3 0.25s together, giving you a total possibility of 0.75 for tossing any head. That's pretty much it as far as tree diagrams go. If you want to find the probability of a given path, you're just going to multiply along each of the branches. If you want to find the probability of multiple paths, then you're still going to multiply along those branches, but you're going to add the paths at the end. Sometimes tree diagrams can be a bit hard to work with if you don't simplify things down. In this example, we have 3 possibilities for each stage, and if you were to draw each of these branches by hand, that would take quite a while. Instead of doing that, my recommendation is that you only draw the branches that you care about. In this case, we're only looking for outcomes that are greater than 1. So all we're going to do is look at our massive tree diagram here and start pruning it. We're just going to look at all the possibilities that aren't greater than 1 and just get rid of them. So already we can ignore the entire top half of our tree diagram because that first element was not greater than 1. All we're going to do from here is erase all the other ones that are in the tree diagram. And when you look at this result, suddenly your tree diagram is much easier to draw. Now, obviously you wouldn't already have this picture, you would have to do this in your head, but the same principle applies. Only draw the things that are particular to the specific example that you're trying to solve. One other quick tip to make sure that you do this right is to make sure that you don't forget the true probability of each given branch. There is still just going to be a 1 in 3 chance of going down any of these branches. And that's because there were 3 numbers in total that could have been selected. Now, just because that isn't shown in the tree diagram doesn't mean that you don't have to represent that. The only reason we're not showing it in the tree diagram is because we want to simplify the amount of effort that we're putting into it by hand. Anyway, Now that we've simplified our tree diagram, we're just going to multiply along each branch and then add all the individual paths together. The good news about this is that we've already simplified things ahead of time. We don't need to think about what paths we need to take anymore. We already did that. These kinds of questions are those where the probabilities along each branch will change depending on what came before. So, just like before, we're going to start by figuring out what are the potential outcomes for our experiment. And in this case, we're either ordering a pie or ordering a coffee. We're told to start our tree diagram with a coffee, and we have to fill out an additional 2 stages because we're looking at 3 days in total. Now we have to fill out the probabilities, and we do that by looking at what happened previously. In this case, we started with a coffee. Hence, to fill out the next day's probabilities, we have to look at this statement here. We're told that the probability of ordering a coffee on the next day is going to be 0.5 if she ordered a coffee on the previous day, which is what happened. From there, we can assume that the other possibility must also be 0.5, since it's the only other possible outcome, and all outcomes in a given experiment need to add up to 1. Now we have to fill out the final day. The good news here is that if we start with coffee again for that final day, then all we have to do is copy and paste that first set of branches, because once again, it's the exact same scenario. We started with a coffee. However, if we instead start with a pie, we now have to refer to this statement here. The probability of coffee has now jumped to 0.8 because we started with a pie on the previous day. From there, we can also say that the probability of pie on that next day must therefore be 0.2 because, once again, all the possibilities have to add up to 1. And just like that, we filled out our tree diagram. This is a very common type of question, so keep this structure in mind. This whole idea of being able to copy and paste the previous set of branches and then change things up for the next bit. This kind of structure appears a lot. But anyway, from here we're just going to answer the question, which in this case is just figuring out what's the probability of ordering a coffee on that 3rd day. Well, there's 2 outcomes for that. So all we're going to do is multiply along the branches and then add each individual path at the end. Some experiments aren't easily described using a tree diagram. Under these circumstances, you might consider using a sample space table. There is no real generic sample space table, so to explore this, we're just going to go through a few possibilities using a dice example. Here, we're interested in the possibility of rolling the same number twice. Drawing a tree diagram for this would take forever, since there's 36 different outcomes. So let's use a table instead. The top row and column will be used to identify what dice was rolled, and each cell in between is just going to be the combination of those 2 numbers. From here, you can see a pattern that very quickly emerges. You can imagine how writing this down would be quite quick because all you're doing is incrementing a given number. In some cases, you don't even bother writing out the full table if you can already picture it in your head. But anyway, we're looking for the possibilities that ended in the same number being rolled. And when you look down that diagonal, you'll see that there are only 6 possibilities out of a total 36 where that happened. When that simplifies, you'll see that the probability was just 1 out of 6, which in hindsight makes a lot of sense. There's a similar thing going on here, but this time we're looking for the addition of our 2 dice rolls to be greater than 8. So when we fill out our table, we're not going to write the combination anymore, but we're going to write the addition of those 2 numbers. Once again, you can see this pattern is very easy to replicate. Once you have your first number, you're literally just adding 1 every single time you go down or to the right. So once again, having filled out the table, all we're going to do is look for all the outcomes that were greater than 8. Then we're going to divide that number of outcomes by 36, the total number of possible outcomes, and when that simplifies down, you're going to get a final probability of 5 out of 18. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.